Good morning, good afternoon everyone! Today in this Godot tutorial, we're going to see how to implement the basic mechanics of a 2D tower defense game. By the end of the tutorial, our little prototype will look like this. We'll have pirate ships that follow a given path and try to escape our cannons to attack the nearest town. So it's our job to place some additional defenses to stop them. Basically, if we have enough coins, we'll be able to pass in build mode and place some new towers on any ground tile. Then those towers will have a given field of vision, and whenever a ship enters this circle, it will be designated as the new target for the tower. The building will then fire some cannonballs in the direction of the ship at a regular rate. In this tutorial, we will keep things simple on the data side and only consider one type of tower, one type of enemy ship, and some predetermined parameters for the attack range, the attack rate, the HP, and so on, that we'll define directly in our scripts. In a real game, however, you'd probably want to extract this data to external files to make it easier to change and tune. By the way, don't forget that the GitHub repo with all the code and the assets for this tutorial is available over here. And now, with this quick intro in mind, let's see what we are starting from and how the project is set up so far. Before diving in, we'll have a quick look at our current project assets and scenes and see what tools it relies on. My main scene for this tutorial will be structured like this. The root node is a simple node 2D with a GameManager.cs script attached to it. Its first child is a camera 2D. This will be useful to properly adjust the zoom of the render to match the size of our level. For example, here you see that my level is actually twice the size of my screen, so I've set my camera 2D node with a zoom of 2. Then I have an instance of my actual level contents. By separating this data in another scene, namely level01.tscn, I get an easy-to-update system where I can just switch this reference for another one and instantly get my game with another level loaded in and all the rest of the components still properly in place. Finally, I have a few UI elements like the coins and lives label in the top left corner and the tower build button in the bottom left corner. We will see very soon how to access and update these objects via our scripts. Now, if we edit the level scene itself, we see that it contains three main parts. At the top, I have a timer called Enemy Spawn Timer. As the name implies, this is a timer node that will periodically send a signal to my level manager script, hooked over here to my root node level01, and tell it to create a new enemy ship. The heart of the level is this time map sub-hierarchy, with 4 overlapping time map nodes. I've actually already discussed this concept of time map in a recent Unity C# tutorial I published, because this tool is common to several game engines. Basically, the whole point of time maps is to facilitate the creation, addition and interaction with 2D levels composed of small units, the tiles, which have both a visual and a position in integer coordinates, with respect to this large grid. By putting several time maps on top of each other, like this, you can isolate the context and better define the layer of each of your time map elements. Typically, in my case, it is important to separate the ground tiles from the rest, so that I can easily check if the player is trying to place a tower on a valid tile or not. By the way, all the tile images I'm using here are from the amazing Kenny library, where you can get hundreds of asset packs for free. Anyway, last but not least, at the end I have a path to the node with this curve already defined. If you're curious about how this node works exactly, then have a look at this other tutorial I made recently on how to create a waypoint system in Godot and C#. In a nutshell, the idea is that by adding children nodes of type pathFollow2D, we can then auto-move an object along this curve very easily just by incrementing an offset. In our case, the objects who will move will be the ships. Those will be instantiated dynamically in our code at runtime as a reaction to the tick of the spawn timer from before. And the asset itself simply contains the famous pathFollow2D node as the root, a sprite for the visual, and a basic area 2D and associated 2D collision shape. Note that the pathFollow2D node currently shows a warning because it is not inside a path 2D, but that it actually will be once this asset is instantiated inside this part of our level hierarchy. Okay, but how exactly will this spawning and movement work? Time to implement our first tower defense feature and see how to handle these ship mechanics. We know that our ship's route is a path follow 2D node, which will allow us to place it as a child of our level path 2D curve and move it easily. To automate this movement, however, let's create a new C# script called shipmanager.cs and place it on our root node in the ship scene. In here, we'll cache a reference to the path follow 2D node in the ready function and then define an arbitrary value for the movement speed. Then all we have to do is, inside the process method, which is called everyFrame, increase the unit offset property of our path follow 2D by a little amount to move our object along the curve. I'll use a small factor to artificially decrease the overall speed and get a more manageable speed in the game. I prefer to extract it from the actual speed variable because this allows me to define this ship parameter as a basic unitary value, and it will make it easier to scale the data for other types of ships if I ever add any. Also, it's essential to remember to have our ship manager derived from the pathfollow2d C# class, and not the default node. Otherwise, the engine won't be able to retrieve the pathfollow2d component on it when we call getNode in our ready function. Okay, so our ship will now move on their own along this path as soon as they are in the scene, except that for now we haven't instantiated any. To take care of this spawning process, we will go back to our level scene and select our enemy spawn timer node. Then in its node tab, we'll connect the timeout signal to a new function in our level manager script on enemy spawn. Remember that Godot's autocomplete feature is not yet perfect for C#, so you'll need to put the auto-generated function back inside the level manager class. Then we'll just declare a reference to a ship asset with a packed scene variable, and another to our path2d node. And in the onEnemySpawn process, we'll create an instance of the ship scene and add it as a child of the path. Don't forget to expose the packed scene variable in the inspector by giving it the export attribute and rebuilding your solution in the MS build panel so it actually appears, and then drag in the ship scene. Now, if I run the game, I see that I regularly get a new ship that spawns on the left of the screen and then slowly slides on the curve I define in my level scene. Because the timer is in its default repeat mode, we keep on getting more and more ships. The only problem is that although in edit mode we can see the path the ships are going to take, it is not that clear when in play mode. Godot path nodes don't show up in actual game builds, so we should add a bit of logic to create our own path visualizer and help players anticipate the course of the ships. Because we want this display to be generated no matter which level data is loaded, we will do that back in our main tutorial scene. The trick for this will be to use Godot's really nice 2D drawing feature, which in short is a way to go beyond common node renders and create more custom visuals of our own. Whenever you create a 2D or a control base node, i.e. a blue or green node, then any script slapped on it will be able to override the draw function. This function is called once automatically at the start by the engine, and the drawing commands are then cached for further re-renders. So let's make a new basic node 2D in our main scene hierarchy called levelPathDisplay and give it a new C# script, levelPathDisplayer.cs. Again, make sure that this script inherits from node 2D and not just node. Then in this class, what we want is to get the path2d node inside our level instance and extract its curve data. Be careful because here, for simplicity, I'm using a direct handwritten reference to my path2d node, which implies I have renamed my level scene instance to this exact string, level. Now that we have our curve, inside the draw function, we can use its points to define a polyline. We'll also pick a light white color, a thickness for the line, and enable anti-aliasing. And there we go, if we run the game, we see that our path is now displayed in play mode too, thanks to this new drawing pass, which makes it easier to understand and predict the route of our enemy ships. That's pretty cool, we've got our ships spawning on one side, then sailing along this line, and finally exiting the screen at the other end. But there's an issue. If you look carefully, you'll see that whenever a ship gets to the end of the path, it actually loops back to the beginning. That's why you have those overlapping instances at the start of the path. So let's fix this and prepare a very basic global game routine by setting up some mechanics in our game manager script and handle the case where ships manage to slip by our towers like here. We said before that in our main scene, the root node base has a script hooked on called GameManager.cs, but at the moment this script doesn't do anything. So we're going to update it to have it keep track of the current number of coins and lives the player has, reference some useful UI elements, and then prepare a util function, updateUI, to re-update these labels with our current coins and lives values. This function will be useful in 4 cases. When we first start the game and get in our ready function, if a ship passes our defenses and gets to the end of the path, if we kill a ship and loot some coins, or if we buy a tower and decrease our coin amount. For now, we can already take care of the first case easily, like this. And we are going to have a look at the second one in more details. We know that we want this game manager script to do something, namely here update the lives counter and then update the UI, whenever a ship instance reaches the end of the path. To do this, we can think of 2 solutions. Either we stick to Godot's signal system and dive into how to set up autoloads to create a global signal system, or we rely on basic C# singletons and turn our game manager into one. The first solution is interesting, but I feel it is a bit overkill for our case. If you want to learn more, however, you should definitely have a look at this tutorial by GDQuest. Here we'll go for this singleton pattern, which is basically a way to keep a global, easy-to-access reference to an object in your code by caching the reference once and then reusing it for further calls. This design pattern can sometimes be a bit of a burden, because it inherently ties together your singleton with all the other parts of the code that use it, and by definition it means that you will have only one instance of this specific object type. But in our example it makes sense, because we'll always need one and just one game manager instance per game. So let's declare a public static variable of game manager type in our game manager script, called instance, and assign it this script instance in the ready function. This means that now any other script can call GameManager.instance to refer to this exact instance of game manager, and thus interact with the global game manager entity. In particular, let's say we define an onShipPassed function in this game manager class to decrement our lives counter and update the UI. Then we can go back to our ship manager script, and if in the process we reach the end of the path, call this function by using our singleton. I'll also take this opportunity to delete my game object so that it doesn't take up useless resources by calling the queue_free method available for all Godot nodes. To check if I have reached the end of the path, I just need to see if my current normalized unitary offset along the path is equal to or greater than 1. However, because for now the path is set up to loop by default, this will never trigger, as the ships will instantly be teleported back to the beginning of the path. So to finish our feature, we need to untick the loop property over here, to ensure the ship only does the journey once and reaches the endpoint. If we restart the game, we see that our ships now sail towards the end of the path, and when they reach this point and exit the screen, they disappear and the lives counter in the top left corner decreases by 1. But of course now we want to strike back and defend the poor city that these pirates are aiming for. So it's about time we discuss our core mechanic: tower placement. Now that the ships spawn and move properly, and that we have a basic UI, we need to take care of our tower building feature. The idea will be to have our button in the bottom left corner toggle on the build mode, and enable a ghost tower visual that follows the mouse to show us the expected position of the tower. You'll notice that this position isn't continuous, it is rounded up to the nearest tile on our timer grid. And depending on whether we are hovering a ground tile or not, this ghost visual lights up green or red. Finally, when we click while over a ground tile, we'll be able to place a tower, which will consume an arbitrary amount of coins and exit build mode. Okay, first of all, let's go to our level manager script and define an override for Godot's built-in input function. This method allows us to quickly react to any player input event, and we can determine the specific type of event to look for by using a C# pattern matching is expression. For example, here my first if block checks for a left mouse button click on release, and the second one checks for a simple mouse move. I'm then going to declare an isBuilding boolean flag and set it to true for these first tests. Ultimately, we'll need to connect it to the UI button, but for the moment it will make it easier to try out our feature and iterate on our design. Inside my mouse move event logic, I'll get back to the current position of my cursor in global 2D coordinates, and this is basically a vector2 value that goes from 0, 0 in the top left corner to the screen width and screen height in the bottom right corner. And it also takes into account the potential camera 2D zoom. So now suppose we go back to our main tutorial scene and instantiate our tower to place scene inside, like this. And then we reference it in the level manager script. I'll directly grab the script on its root node, the tower to place manager, and I'll again write the whole path by hand, assuming this is the exact name of my tower to place scene instance in the main scene hierarchy. If we now assign our mouse path variable as the position for this node, you see that in-game, the ghost tower now follows the mouse perfectly. To actually have it stick to the tilemap squares, however, we need to round this mouse position vector to snap it to the closest tile size multiple. This is a fairly common game dev logic. In a nutshell, you just have to define your rounding step value, so here it's the size of my ground tilemap cells, and then divide, floor and remultiply your initial continuous vector, as shown here. This rounds position to tilemap thus transforms a 2D vector into its snapped equivalent. If we apply it to a mouse path variable and use this new rounded value for the position of our tower to place instance, we see that the ghost tower indeed snaps to the corners of our tilemap grid. To actually have the tower be in the middle of a tile and not in its top left corner, we'll just add a little offset that is defined as half the size of a tilemap cell on both the X and the Y axis. So we now have an easy-to-use tool to prepare the position of a future tower. The next step is to check whether this position would actually be valid for a tower, and adjust the color of our ghost tower accordingly. If we are currently hovering a ground tilemap, it should be green, and otherwise it should be red. The tower to place manager already has a method to handle this logic, called setValid, which takes in a boolean parameter to indicate if the position is okay or not and adapts the color. So what we need to do in our level manager is check for the validity of the current placement, and then call this method on our tower to place instance. To know if our current target position is okay or not, we are going to proceed in two steps. First, we'll convert our rounded coordinates from the world space to the cell space. Remember that those are integer values that start at 0, 0 in the top left corner and then increment steadily along the X and Y axis for each tile in our tilemap grid. For example, in my case, since my tiles are 128 by 128 pixels, the cell coordinates will be the nearest integer value of the world coordinates divided by 128 on both axes. The second step is to check if our ground tilemap actually contains a tile at this converted position or if it has an empty space here. If there is a tile, then the position is valid, else it is invalid. We can verify this easily by using the tilemap's getCellV method and checking its output against -1, which is the value of an invalid or an empty tile in a tilemap. I'll store this result in another boolean flag, tower has valid placement, because we will need to reuse this value when we actually try to click and place the tower to see if building is really possible. Then I'll simply call my tower-to-place.setValid function with this boolean, and it will automatically update the color of the ghost tower properly depending on whether I'm over a ground tile or an empty space with just a sea. Okay, now that we can anticipate the tower position, let's handle the placement in the click logic. We'll look at our isBuilding and tower-has-valid placement booleans, and if everything checks out, call a new placeTower function at the resnapped mouse position. In this placeTower method, we will want to instantiate our tower scene. So we'll need a reference to this asset as an exposed parked scene variable, which we need to remember to drag to the inspector. And then in placeTower, we will position the instance at the given location and add it to our level hierarchy. This tower asset also requires a bit of initialization, in particular to properly set its field of vision to match the one of a tower-to-place instance. Of course, in this first prototype version, everything is hard-coded, therefore we could skip this part entirely. But if we ever want to have multiple tower types, then we'll need to have this mechanic in place, so better take care of it now. If you take a look at the Tower Manager script, you'll see that it contains an initialize method that receives a reference to the level manager in charge of this object and the radius to use. The logic in this method takes care of updating the size of the FOV area to this shape to match this given radius. What this basically means is that in our level manager, when we create a new instance of this tower scene, we have to get the Tower Manager script on its root and call its initialize method with our current level manager script instance and the radius of the tower-to-place variable like this. There are two things we need to do to finish this feature. Reset our isBuilding flag and hide the tower-to-place instance to exit build mode, and decrease our coin amount by the cost of a tower. For the isBuilding flag, I'll declare a new function called setIsBuilding that updates the value of the variable and shows or hides the tower-to-place object accordingly. I'll then use it in the ready and in the placeTower functions. For the coins, we can once again take advantage of our Game Manager singleton. If we declare a new method in the Game Manager script to try and buy a tower, if we have enough coins, we can then call it from the level manager when we click. I'll make sure to return a boolean from this function so that I can know if I had enough coins to place the tower and should indeed call my placeTower method, or if I aborted early. We can now run the game and move our ghost tower around to choose a valid spot, and then place a tower somewhere on the ground, which immediately hides the ghost tower and consumes an arbitrary amount of 20 coins. Let's now see how to link this build logic to our UI button in the bottom left corner. Instead of enabling the build mode when the game starts, we want it to be controlled by this button. So in my ready function, I'll first change my call to setIsBuilding and pass in false. Then just after that, I'll list all the UI tower buttons in my scene and connect the pressed signal dynamically. This will allow me to easily add or remove new buttons if I ever have new tower types without having to worry about setting up the signals. When I press my tower button, so in the callback function for this signal, I'll call my setIsBuilding method with a true parameter. I can even check that I have enough coins at this early stage by creating a quick check function in my game manager and using it in the onTower button mouse pressed method. And here we go, we now start in normal mode with no ghost tower visible, and if we click the UI button, we enter build mode and get back our logic from before. There is however a little problem you can see here. If I'm in build mode and my mouse gets over the UI button or over an existing tower, the ghost tower doesn't disappear, and the placement is still considered valid. What we'd like is for those areas to stop any build from happening. So to wrap up this section, we will do a little fix for this by adding a second boolean flag in our level manager class, canPlaceTower, with an associated setter function. We'll make sure that when we change the value of our isBuilding or canPlaceTower variables and toggle the ghost tower visual, the other flag is also consistent. And in our mouse click logic, we will also check that this new boolean is true. Then, still in the level manager, we are going to come back to a loop on the UI tower buttons at the beginning, and in addition to the pressed signal, we're also going to dynamically connect two other signals, the mouse entered and mouse exited. Those functions will turn our new canPlaceTower boolean on and off. We see that now if we hover the UI button in the bottom left corner while in build mode, the ghost tower temporarily disappears and then comes back as soon as we exit this area. We can do something very similar in our tower asset by opening the scene and connecting the mouse entered and mouse exited signals of its root area to the node to call back functions in the tower manager script. Those functions will directly call the setCanPlaceTower method of the associated level manager script. And that's it. Our build mode now properly toggles on when we click the UI button at the bottom. It allows us to place towers on ground tiles by left-clicking, and it consumes 20 coins out of our initial amount. We also temporarily switch off tower placement if we hover the UI button or an existing tower. So we can now populate our level with towers, which is great. But at the moment, those towers are quite inefficient, since they don't fire any cannonballs on the enemies. That's why we have to implement the last feature of our basic tower defense game, the firing of cannonballs and the destruction of the enemy ships that happen to encounter their route. For this final part, our goal will be to give some additional logic to our towers, so that when a ship enters their field of vision, they add it to their list of targets, mark the first one as the current target, look at it continuously, and regularly fire some cannonballs in its direction, at a given attack rate. Those cannonballs will fly in a straight line until they either meet with the ship or exit the screen. In both cases, they will disappear, but if they touch a ship, the ship will lose 1 health point, and if the ship reaches 0 health points, it will die, disappear, and grant us an arbitrary amount of coins as a reward. For all of this process, we will rely a lot on area 2D nodes. We already used them a bit in the previous sections, but as a quick reminder, the way it works in Godot is that you have an area 2D node that can detect and signal various types of collisions, or object entries and exits, and the shape of this area depends on a child node of type CollisionShape2D. In my case, I have 3 areas, which are all disks. The tower scene has an area 2D node as its root that covers just the size of the sprite. This is the area we used previously to detect the mouse in and mouse out events. The tower scene also has another area 2D to represent the field of vision, which size is auto-configured by the initialize function of the tower manager we discussed earlier. And the ship scene has an area 2D node that matches the size of its sprite, and that will be able to detect the encounter of a cannonball. The cannonball scene itself doesn't have areas, but it is a kinematic body 2D, which will make it easy to move with a constant velocity and easy to detect for a ship's area 2D node. By the way, I've also ensured that my various areas and bodies all reside on different layers and look for the proper masks, so that objects don't detect themselves and are instead tuned to monitor a specific type of entities. More specifically, the cannonballs are on layer 2, therefore the ship's area 2D node monitors the mask 2. The ships are on layer 3, and therefore the tower's field of vision area 2D node monitors the mask 3. This setup makes it quite straightforward to implement a whole firing and hitting logic. First, we'll go to our tower scene and connect the field of vision area 2D nodes, area entered and area exited signals to new callback functions. In those functions, we'll get back the node 2D that entered the area, and that is necessarily a ship thanks to our layers and masks, and then we will add it to or remove it from our list of available targets. We will also keep track of the current target so that it is always the first target in the list, if there are any. We'll define both of those variables at the top of our tower manager script and initialize them in the ready function. Remember to import the system.collections.generic package to be able to create a list of node2 like this one. Then in the process function, we'll say that if we have a current target, then our cannon sprite needs to look at it. This will make the cannon follow the target smoothly. Finally, to handle the firing mechanic, we'll make a little counter that decreases down from the attack rate to 0 whenever we have a target. When this counter reaches 0, we'll fire a new cannonball and reset the counter to the attack rate variable. Firing a cannonball will be done in 3 steps. To begin with, we have to create a new instance of our referenced cannonball asset scene and position it at the same location as our tower. As usual, remember to assign the cannon asset in the inspector. Then we need to initialize the cannonballs with a given velocity, a damage amount, and a speed. The damage and the speed will be defined on the tower and not the cannonball directly, because this way, if one day I implement some upgrade mechanic for my towers, it will be easier to update those parameters and pass them on to the new cannonballs. The velocity is a bit trickier. A naive approach is to simply normalize the difference between our current target's position and our own position. The problem is that if we do this, since the ship keeps on moving while the cannonball is flying, our tower will systematically fire too far behind. If the cannonball is really too slow, or the ship is really too fast, we'll therefore miss our target every time. To avoid this issue, we can do an educated guess and try to predict the future position of our target by offsetting it slightly by the current direction of the ship. This factor of 50 is an arbitrary number for the length of the offset, and don't forget that since we're working in 2D, everything is done in pixels, so 50 is not that much. Finally, we'll insert this new node in our game hierarchy at the root of the whole scene tree, to avoid any unexpected parent-related transforms. Once instantiated, our cannonballs will automatically move in a straight line using the velocity we initialized them with. The cannonball manager I hooked on them will take care of that for us. So we don't have to do anything for that part. And the last step is to handle the ship side and check for collisions and possible distraction. So let's open our ship scene. We also want to connect one of the Area2D node's signals to a callback function. But this time, since our cannonballs are kinematic bodies and not areas, we'll hook up the body entered signal. I'll create a new onArea2D body entered callback method, and in here I'll get back the cannonball manager script from the object that triggered the event. Again, we know it will be a cannonball thanks to our layers and masks. Now all that's left to do is retrieve the damage points our cannonball does, apply it on our ship to reduce its health points, and destroy the cannonball by calling its Q3 method. In the TechHit function, we'll check to see if we reach 0 health points, and in that case, we want the ship to die. This means that we will call another function on our game manager singleton instance, onShipDied, and pass it this instance, and then destroy our ship object. The onShipDied function will just increase our coin amount by the reward for this ship, and update the UI. And we are done. If we restart the game now, we see it contains all of the basic tower defense mechanics from the original demo. Ships spawn on one side of the screen and start to move along the path we've drawn using the curve tool, and we can predict their course thanks to our hand-drawn polyline. Then, if we click on the UI tower button in the bottom left corner, we enter build mode, and we can buy some towers by moving our mouse to a valid tile and left-clicking. To help us with the tower placement, we have this ghost tower that follows the mouse, but snaps to the time-up grid. We've also made sure that when we hover an existing tower or UI element, this ghost tower temporarily disappears. If a ship reaches the end of the path, then we lose 1 life, as shown by the UI counter in the top left corner. But if a tower sees a ship enter its field of vision and manages to fire cannonballs at it, then it will lose health points and eventually die, giving us some coins as a reward. So there you are, you've now got the basics for implementing a simple 2D tower defense game in Godot and C#. I hope you enjoyed this tutorial and that you learned a few things. If you did, feel free to like the video and subscribe to the channel. And of course, if you have other ideas of Godot tricks that you'd like to learn, Or if you want me to continue this series and explore more features for this game, don't hesitate to leave a comment. As always, thanks a lot for watching, and take care.